All right, good morning, everyone. You all doing okay today? All right. All right, so we were talking last time about inverse functions. It's what we kind of ended class with, this idea of trying to find an inverse. Now, what I thought we would start with today is kind of what the end goal. All right, so what the reason why we're going to be talking about inverses. I thought if I presented you with a problem that we're going to be able to solve at the end of class, it might help motivate why we're doing what we're doing. Okay, so I want you to look at these two questions. The first one, $3,500 is put into a savings account at an interest rate of 2.3%. If interest is compounded continuously, then how much money is in the account after 3 years? So this has to do with simple interest. And we talked about the different formulas. I gave y'all two formulas for doing this. And if we saw the word continuously, that we would be using that shampoo formula. So for this first one, we know that we would be using the formula A equals P E raised to the R times T. And we know how to do this. We've gone through a problem like this, but I want to set it up and I want us to see something here. So if we do this, the P is how much money we start with, right? So I can say, all right, the amount that we'll have will be the 3,500. And then we'll have E, which is that special key on our calculators, right? And then we have the interest rate. We have to write the interest rate, R as a decimal, so 0.023. And then we multiply that times T, which is the time in years. So we put 3 here. Is everybody clear on that? Any questions on that? I'm going to go ahead and do this on my calculator just to get an answer. You know, I'm not going to go through it in detail, but just so we have an answer. 0.023 times 3. If you did this, you should get approximately $3,750 and like 2 or 3 cents, something like that. Okay, so we know how to do that. If we know the amount of money that's going in, we know the interest rate, and we know how long it's going in for, we can determine how much would be there at the end. But in the real world, a lot of times you don't want that. That's not what you want, okay? What you want is to know something like how long you need to leave the money there or what interest rate you need. So look at the second question. We wish to put $3,500 into a saving account for 3 years. So it's the same as the problem before, but it says if the interest is compounded continuously, what interest rate do we need? Okay, in order to have $5,200 at the end. So that's a different question. See, we don't know what the interest rate is. Now we are told that we're compounding continuously, so we can still use this formula. Okay, we can still use that formula, but look at how it changes. We still have that P is 3,500. We still have E, but this time we do not know what the rate is. We don't know the interest rate, right? I highlighted it that in blue. Since we don't know what it is, I'm just going to put R here because I don't know what it is, times the number of years, which is 3. And what do we want this to turn out to be? This is important. What do we want this to be at the end of the 3 years? How much money do we want?
5,200.
5,200. So the 5,200 is actually the amount that we want at the end. So what we do is we say we want this to equal 5,200. Do y'all see the difference between these two? In the first problem, we were trying to figure out how much would be there at the end. And we were given all the other information. Here, we know how much we want at the end. We know how much we started with. We know how long we're leaving it there, but we do not know what the interest rate is. So I'm going to write this just one more time. We have this, 3,500 E. Now, R times 3 is just 3R. I'm just going to write as 3R equals 5,200. And the question becomes, how do we solve this equation? We want to know what R is, right? So how do you solve for R, right? How do you solve for R? there has to be some way of algebraically solving this. Now, right now, if you've never seen logarithms before, it's impossible to solve this equation. There's only one way to do it. You have to have logarithms. So let me kind of stress that to you. Right now, I'm just going to put a big question mark. We don't know how to solve it. And I'm going to illustrate why we don't, okay? The only equations we know how to solve right now are these. We can, when it comes to equations, we can solve, right? So the things that we've actually learned how to do. First, we know how to solve linear equations. An example of that would be like 2x plus 1 equals 5. So if I asked everyone here to solve this, I would expect you could do that. Subtract 1 on both sides, divide by 2, you can do that, right? I'm not going to go through it, but we know how to do linear equations. We know how to do quadratic equations. If we have something like x squared plus 5x minus 6 equals 0. If we have a quadratic equation, you can either factor it or we always have the quadratic formula. So we should be able to do that also. But if I gave you an equation like this, okay, let's say I wrote 2 raised to the x equals 8. That is not a quadratic equation. That is not a linear equation. This is what we call an exponential equation. And what makes it exponential is the fact that the variable x that we're solving for is up in the exponent. Notice on both linear and quadratic, the x is not up top anywhere. It's always down on the bottom. Do you all see that? The x is not the power. Here with an exponential equation, the x is actually the power. Now, you might be able to tell me the answer to this. Someone might look at that and be like, oh, well, x is 3. Because if I take 2 and I cube it, 2 times 2 times 2, right, that would give me 8. But you're doing that just because you know what 2 to the third power is, right? That's how you're doing that. If I give you something like this, 5 to the x equals 8, then there's no way you're going to solve that. There's no way you're going to be able to tell me what x is. Do y'all see the big difference between the linear quadratic, which we can do, and the exponential? Do y'all see the huge contrast between the two? Like 5 raised to what power gives you 8? Now I'm going to tell you what the answer is real quick, just so that you have it. Hold on. And then our goal here today will be to figure out how I did that, right? Like how in the world did you solve that? So the answer here is actually 1.292. So I had to use my calculator. So you can check this. If you take 5, and if you have your calculator, try this. Raise it to the 1.292, and you should get a number really close to 8. It's not going to be exactly 8, but it's going to be really close. I get 7.9996. So it's close, right? So how in the world did I figure out 1.292? So that's what today is about. How do we go about solving things when the variable we're looking for is up in an exponent, okay? And if we go back to the question right here where I was saying, hey, how do we solve for r? Do you notice that the thing we're solving for, the r, do you see that it's up in an exponent? It's up top. So because it's up top, that's exactly like a problem like this. So how do we do it, right? So that's what today's about. I hope that that helps in terms of like, why are we doing this? Okay, so when it came to inverse functions, when we were talking last time, the whole idea about an inverse was that it takes a function back to where it came from. So I gave you an example. The first example I gave you last time was 2 times x. Let's just look at this. Last time I said, okay, if we're given the function 2x, it'll take 1 over to 2, it'll take 2 multiplied by 2, you get 4, take 3 multiplied by 2, you get 6. And we were asking, how do we undo that? How do we come up with a function that would take all these numbers back to where they came from? And so we said, well, we just have to take half of the number, right? If you take half of 2, you get 1. If you take half of 4, you get 2. Take half of 6, you get 3, right? So this function is the inverse of this one. It undoes it. So today, what I'd like to do to start here with this idea of inverse is I want to look at one function in particular, and then let's try and find its inverse. So the function that I want us to look at is the very, very important one, e to the x. And the reason we're going to be looking at e to the x is because that's the one that we use for our continuous compounding formula, the shampoo formula. That e is in there, right? So if we could find a function that undoes this function, we're going to be in business. So we did this in class last time. In fact, I think I'm just going to go grab it. Where is it? There it is. I'm just going to grab this right here because we I don't want to have to redo this table. So I had you get on your calculators and do this. So I'm going to just pop this in right here. Okay, so we know that when you plug in -3 into this function, you get 0.049. When you plug in -2, you get 0.135. -1 goes in, you get this, right? So a picture of this would be that the exponential function takes the number -3 and sends it over to 0.049, takes -2, sends it over to 0.135, and we could keep doing this. I'm not going to do them all. Let me see. It takes 3 over to 20.085. Are we good on that? Now, the question is, can we find a function that would take it backwards? And I used this notation last time with a little -1. Is there a function that exists that takes everything back? And the answer is yes. It's called the natural log. The natural log. And there's a key for it on your calculator. It looks like this right here. So look for that key on your calculator. A lot of people think that that's IN, like we're going to go inside. It's not IN, it's actually LN. And it comes from natural log. When you say natural log, if you were to use French, like if you were to speak in French, you would say log natural. You would say it backwards. So that's where it comes from. It's logarithm natural or something like that. So look for that key on your calculator. And what I'd like for you to do is first plug in 0.049. Okay, so I'd like for you to, on your calculator, do natural log of 0.049. And you should get an answer really close to -3. Well, it's not real close. I'm getting -3.01. Okay, 59, something like that. But do you see that it looks like we found something that took that back to -3, right? Let's do that for the next one. Let's see where 0.135 goes. So take that, plug that in, 0.135, and I get about -2.002, something like that. So it looks like it did what it was supposed to. It took this 0.135 and it took it back to -2. Well, let's just do one more. The natural log of 20.085. If we do that, does anyone have any questions while we're going through this?
Yes, sir. Does it matter if my calculator is in radians or degrees?
It does not matter for exponential and log functions. That would only matter if you were doing trigonometric functions, which we don't deal with in this class. That would be something you have to pay attention to if you ever took a class called pre-calculus.
All right, thank you.
All right, no problem. Okay, so we have a function, okay, that takes everything back. Do y'all see that? We have the inverse. So this is a good thing. So I'd like to now that hopefully I've convinced you that this function right here, this is the inverse of e to the x, we have some properties that I want us to be very clear on, okay? So here are some properties. and these are going to be really important. The first property is this. If you ever take e and you raise it to the natural log of x, you will get x. And what's happening here is that what first happens is that you take the natural log of a number, and then after that you take e and raise it to that power. So it's like if you look at this picture, what's happening there is that you're starting with an x here, you do natural log of it first, it takes it here, and then you take e of it and it takes it back to where it came from. So the idea is that you're putting the two functions together. You're putting the natural log and the e together, and they wipe each other out because they're inverses. That's what they do. Now, if you don't believe this, we can try this on our calculator. On your calculator, take e and raise it to the natural log of 3. Okay, try that on your calculator. Take e, raise it to the natural log of 3, and oops, and I bet you're going to get 3. Y'all see that? Now remember, I expect that you're doing this on your calculator. You don't want to be like the first time you ever do this is when you're sitting there at the test, right? So make sure you have your calculator going at least the next couple of days in class. All right, so that's a really nice property, right? The next property is the reverse of this. If you take natural log and you put e inside of it, e to the x, sorry, you'll get x again. So that's like putting it through the loop the other way around. And so let's try that on your calculator. Specific example, do natural log of e, let's go e squared. And when you do that, you should get 2. Those two properties are extremely important for us, all right? Extremely important. Let me show you now with those properties how we can actually use them to solve some equations, all right? So watch. Here's the first problem. What is, if I tell you this, e raised to some x is equal to 4, can you find what x is? Solve for x. Okay, now first thing I want you to notice here is that, do you see that this is an equation that looks a lot like these two because you have your x up top? Do y'all see that? You have the x up here, and what we're trying to figure out is what do you have to raise e to in order to get 4? Now what I'm going to do is I'm going to use these properties. So watch how I use the properties. What I'm going to do is on the left-hand side of the equation, I'm going to put the natural log. I'm going to take the natural log of the left side. And then remember with equations, whatever you do to one side, you have to do to the other. I'm going to do natural log of 4 over here. Now, why do you think it is that I took the natural log on this side? Why do you think I did this? What's going to happen to this expression right here? What does this turn into? Look at your properties.
Will the x turn into a 4?
I'm sorry, say again.
Will the x be 4?
Well, just look at the left side and just ignore the right side for now. Just don't even look over here. Just if we had e to the x and I took natural log of it, look at your two properties here. What does natural log of e to the x become according to this property?
X.
Just x, right? So do you see that the left-hand side just becomes x? So it's like I started out with this where x was up here. By taking natural log on both sides, I've now dropped the x and the x is by itself. And that's really good because we're trying to figure out what x is. So I know the left-hand side is x and the right-hand side is just the natural log of 4. So now you just do that on your calculator, do the natural log of 4, and that's going to be our answer. I get 1.386. Let's do another one. Okay, let's do another one. Just to make sure everyone's on board here. Another example. What if we do e to the 3x equals 100? Okay, we're trying to solve for x. All right, so you look at this and you first have to realize that the x is up top, right? You see that? The x is up top. We need to get that x down. So what we're going to do is we're going to come in here, we're going to try and kill off the e. The only way to kill off the e is to do natural log on both sides. So I'm going to take the natural log on the left side. I'm going to take natural log on the right side. Anybody have a question here?
Yeah.
Go ahead. Oh, no question? Okay, and we're okay then with this? Take natural log on both sides? Okay, now can somebody tell me what the left-hand side turns into? It's not just x. What do you think?
3x.
3x, good. So again, what's happening here is that the natural log and the e are killing each other off. And then what you're left with is whatever was up there. So if you have 3x up there, that's what's going to be left. And then that equals natural log of 100. So now on your calculator, take the natural log of 100. You should get 3x equals 4.605, something like that. Are we done? No, because this is what 3x is. This is like a linear equation now. Just solve for x by dividing both sides by 3. And you get x equals, let me see, divide that by 3. 1.535. There you go. So if I replace that x with 1.535, then I will get, if I raise e to that power, whatever that all is, then I should get something close to 100. Let's do another one. Just looking here. Okay, how about this? Next example. What if we have 30 e to the 4x plus 2 equals 96. Okay, so these things are starting to look more complicated, right? This is starting to look a little bit crazy now. So I want everyone again to realize that here's what we're trying to solve for. We're trying to figure out what that x is. I did the 4 also, but the main goal here is to solve for x. So I realize that the x is up top, right? It's an exponent. So because it's an exponent, I know I'm going to need a natural log to kill off the e. However, I've got some other things happening here that I need to take care of first. All right. So what we're going to try and do right now is we're going to try and get this whole thing with the e. We're going to try and get that by itself. Let's try and isolate it alone on its own on one side of the equation. So I'll start by subtracting 2 on both sides. And when I do that, I get 30 e to the 4x. And then the 2 went away, so then I have equals 94. Anybody have a guess as to what I'm going to do next if I'm trying to get this e to the 4x by itself? Should I call them?
Would you divide the 30 by 94?
Good. We're going to divide the 30 because that's multiplication right there. So we're going to undo that by dividing by 30. Good job, Taylor. 30 goes away. And now I have e to the 4x equals, and okay, we'll just get our calculator out. 94 divided by 30. It's about 3.133. We don't need to go out that far here. It's okay. Just go out a few decimal places. If you want to go and put all of the decimals, you can. It's up to you. Okay, so now we're at the point that we wanted to be at. I think I will call on people today. That'll be fun for you, right? You enjoy that? I'm kidding, right? All right, so let's see. Okay. How about Jesus? Is Jesus around?
Yes.
All right, you know what we're gonna do next?
IN E 4x.
ln, L, remember, it looks like an I, it's an L though. Think logarithm, okay? Yeah, I don't care if you say IN, I'm just telling you that it's not IN. So you're gonna do that on this side, right? E to the 4x, and then you have to do that on the other side too, right? Jesus? Okay. All right. Now, Jesus, what happens on the left-hand side? Tell me what happens on the left. What are we left with?
4x.
4x. These kill each other off. You've got 4x. Good. See, that's the power of the natural log. It allows you to bring that x down from the top. It allows you to drop it. Now, Jesus, you still have to do that. Do you have a calculator or no? Yeah.
Yes, sir.
Try that natural log of 3.133 and tell me what you get there.
1.141.
Yeah, let's go with that. All right, good. Tatiana, is Tatiana here?
Yes, sir.
What should I do? Am I done? What do I do next?
Divide each side by 4.
Okay, do you have a calculator going or no?
Yes.
Okay, tell me what you get.
I got 0.285.
There you go. That's it. Okay. Good.
Sir, I have a question.
Yes.
So how do we know when to add the natural log? Is it only when we need to cancel out the E?
Yeah. You bring the natural log in on both sides only when you've gotten the E piece by itself. So that's why, see how I highlighted this E in blue?
Mm-hmm.
I needed to get just that right there by itself. You cannot.
So that's why you divided the 30 first.
Yes, that's right. The reason, yeah, it will not work if you were to do it. Let's say you were to take this line right here, 30 e to the 4x equals 94. If you were to do natural log here of both sides, if you did that, the next line would not become 4x because this natural log and e, they don't kill each other off if you've got something in the way here. If you've got a 30 there, they won't kill each other off. You have to have that 30 cannot be there, okay? Good question. I was make sure everyone understands that. That's why we had to divide this 30 out right here on this step. Okay, so believe it or not, we can actually answer that first question that I asked that we were stuck on now. Remember this problem right here? Let's go ahead and take that. I'm gonna just take the whole thing. Oh, no, I'm not. No, I am. I'm gonna start a new page here. So the question was, if we wish to put $3,500 into a savings account, we're gonna leave it in there for 3 years. We know the interest is compounded continuously, but we want to know what interest rate we need to find in order to have $5,200 at the end of the 3 years. So this would be like, you know, we go and we start looking at different banks and we're like, okay, let's see, you know, what interest rates they have. Let's see what interest rate we would need. Let's see if it's even possible to find that interest rate. So we want to know, we want to solve for R, right? R is up in the exponent. So we need to be able to pull that down. So let me call on our next contestant. Let's see, Anastasia. Anastasia here. I see Anastasia. Anastasia, no, going once, going twice. Okay. How about Leah? Leah? See if I see Leah here. I don't see Leah. Okay, how about Beth? Beth Rodriguez? I see Beth. Is Beth actually there?
Here.
Hey, how's it going, Beth?
Good.
Are you following this okay?
Yeah, so far a little bit.
Okay. So Beth, we're trying to figure out what the interest rate is here, right? So we're trying to get that R by itself. Any ideas on what we should do first? Just go for it. Who cares?
Do we bring it down and like put it in the calculator?
Okay. How are you gonna bring that down? There's only one way you can bring the 3R down. You have to do what on both sides?
Divide it.
How do you mean?
Divide by 3,500.
Yes. Okay, good. So look, we want to get this 3R down. The only way we can get it down is if we can get this E thing by itself. We can't get it by itself until we get rid of the 3,500. So we have to divide both sides by 3,500 first. Okay, that's the first step. Now, if we divide 3,500 on the left, that will leave us with the E to the 3R. And then we get on our calculator and we do 5,200 divided by 3,500. Oops. And I get about 1.485, something like that.
Yeah.
Okay. Now, Beth, you can get that 3R to drop down, but what do you have to do on both sides to do in order to have that happen? I mean, you can't just like drop it down. The next line cannot just be 3R. You've got to do something on both sides first. So what is it that we're going to do?
You have to put the I in.
Mm-hmm. There we go, like that on this side, and then we do it on this side. Now on the left side, let's see, we're going to let Kira take over. Kira, how's it going today?
It's okay.
Okay, are you following this?
Yes.
Okay, so what's my new left side going to become? What's the left side? Just the left side of the equation. What happens over there?
It's gonna cancel out each other. It's gonna just be 3R.
3R, yep. And then I see you have a calculator there. So go ahead and give me what the right-hand side is going to become.
It's 0.395.
Good. 0.395. Okay, are you done, Kira? Or is there anything else to do, or are we done?
You have to divide the 3 from the R.
Yep. Divide the 3 on both sides. Good. All right, so I'll go ahead and do that. 0.395 divided by 3. And we get about 0.1316, something like that. Okay. Everyone understand that? Are there any questions? This is our answer, right? This is the interest rate we need. So we need an interest rate of 0.1316. Who's going to tell me what that really means? Who wants to tell me what that means? Because it's a decimal, right? But we're trying to find our interest rate.
Would it be the percentage that they charge the interest at?
That's
all
right.
the
You
time?
said the key word. We're looking for the percent, right? We're looking for the percent that they're going to charge us or that they're giving us for our money. we have this is the answer, but it's not written as a percent. Do y'all see that?
Wouldn't we
It's
just
written
have
as
to
a
put the
decimal.
point?
We've got to go back to a percentage now. So how do we go from a decimal to a percent? What do we do with this decimal point?
You move
Moving
it
it back 2 spaces.
Which way?
to the right.
To the right. So this really means 13.16%. So I can already tell you right now, you're not going to find this bank account. There is no bank that exists on this planet that's going to give you 13% for your money. Nowhere, ever. Okay. In fact, even if you were to invest in something very risky, like, you know, some very risky stocks in the stock market, you'd be lucky to get 13.16%. Okay, so there's just no way that's happening. If you have the expectation of turning $3,500 into $5,200 in 3 years, it ain't happening. Okay, not in just a simple interest account. All right, but now we know that that's not possible. Does this make sense? Okay, let me see here. What else did I want to do? Okay, so how about this? This isn't a good question. I'm going to type it up. Let's go with $10,000 is put into a CD at 4.75%. If interest is compounded continuously, how long will it take to double your money? Oh, geez, I don't know what I just did there. There we go. We're gonna put $10,000 into a CD. Do y'all know what a CD is? It's not one of those things that you put in to play music. That is a CD, but this stands for Certificate of Deposit. And what it is you go in, you put the $10,000 in, and then you agree. Okay, you make an agreement with the bank that you will not come back for that money for a certain number of years. So that money is not yours anymore. What the bank's going to do is they're going to give you interest on that money, but you can only come back for it at some certain amount of time. So like if I go right now, let me just bring this up here. CD rates. I'll show you all this page in a second here. So right now, wow. They're only giving us one answer right now, but this is an example of a CD. If you put a minimum of $500 in, okay, $500, and you do that for 1 year, so you can't touch that money for 1 year, they'll give you 0.65%. That's like nothing. And you can change your term. You can go to higher years. You can, oh, I did not mean to click on that. Let me try and see if I can find some other ones. Here we go. All right. So this shows you a good. So again, a minimum here. Let's look at this one. You have to put at least $1,500 in, and you can't touch it for if you agree to not touch it for 1 year, they will give you 0.6 on your money, 0.6%. But if you agree to not touch it for 3 years, they'll give you 0.85% on your money. If you agree to not touch it for 5 years, they'll give you 0.9. So the longer you agree not to touch the money, the more percentage they'll give you. Does that make sense? Okay, so now I gave you a rate of 4.75. Look, do you see that nobody is going to give you 4% for a CD? Do you see that? It's just not going to happen. All right. But I just want to make up a problem. So, all right, here we go. $10,000 is put into a CD at 4.75%. If interest is compounded continuously, how long will it take to double your money? So we know we're going to be using this formula. And what I'd like to do is I'd like to now allow everybody here the opportunity to take a few minutes to see if you can figure this out on your own. All right. And I'm going to highlight a couple of things here, or just one thing. How long is a measurement of time? That's what they want to know. How long, right? So we're solving for t in the problem. You need to figure out what all the other pieces are, plug them in, and then go solve for the t. And I will also highlight this, double your money. That actually means something here, okay? So let's take just a few minutes and then I'll come back and see, I'll call on the next person and see if they've worked through this or not, all right? See, it's 10:13, let's say 10:16, I'll see where y'all are. Okay. Abigail is up. Abigail De La Rosa.
Yes, I'm here.
How's it going?
It's going good. How about yourself?
We can't wait for the weekend.
I know, me too.
Going okay considering everything that's going on in the world. So what do you got? Did you figure any of this out?
I mean, I made the formula, like I plugged everything in, but I've been using like the calculator on my phone,
Mhm.
and sometimes I get confused on like what buttons to press. So far I have the formula, so it's A equals 10,000 E, and then to the power of open parentheses 0.475 times T close parentheses.
Okay, good. Now, you said 0.475, is it did you have 0.4 or 0.04? Be
Oh,
careful.
0.04.
Yeah, 0.04, okay.
Sorry.
I agree with that. No, good. I just want to make sure. All right, so everyone, we're putting $10,000 in, so that's P, right? E is always going to be E. The rate, okay, so Abigail saw the rate was 4.75%, convert that to decimal. Time is what we don't know, so we leave it as T. Now, Abigail, how much do we want this to be at the end?
20,000.
20,000, okay, so that's something everyone has to understand from the word problem. We want to double our money, right? Okay, good, that's perfect, that's perfect. Now, you want to keep going?
Yeah, so I would then divide both sides by 10,000.
Yep. Good.
So then you're left with E to the power of 0.0475 times T equals, what is that, just 2?
Yeah, it's just 2.
Okay. And then you bring in the natural log, correct?
Perfect. Yep, natural log on both sides.
So then you're just left with 0.0475 T is equals to the natural log of 2. And then you just divide both sides by 0.0475.
So I'm going to write what natural log of 2 was, just so everyone has it here. And then you said you're going to divide both sides by 0.0475. Good. 0.0475. So T would be, did you get something, or is this the part you're having trouble with your phone?
No, I just had trouble with the natural log of 2, but you put that in already. So I got 14.58.
Yep. So if you are having trouble, this goes for everyone, if you're having trouble getting from natural log of 2 to 0.693, make sure that you get that figured out before we have our next test, right? You don't want to be like on the test and you know what to do, you just can't get the number because you can't figure it out on your calculator. Every calculator is a little different. Some calculators, you actually hit the natural log button first and then put 2 in. And other calculators, you hit the 2 first and then hit the natural log. That's a lot of phones work that way. But anyway, all right, that's our answer. Good job, Abigail.
Thank you. It was 5.8, by the way, sir.
It was 5.8. Oh yeah,
Yeah, that's.
Yeah, thank you.
Mhm.
But that's, I mean, look at that. That's 14 and a half years, right? This is years. So and that was a good, that CD, that was like just an outstanding interest rate, right? That was really good. 4.75, that's a very good interest rate. In fact, if you find a CD at 4.75, let me know. Right, because you're not. But that means in 15 years, you double your money. You double your money. Now, just out of curiosity, what if this was not 10,000? What if this was $1 million? You know, just say we had $1 million. Do you think it would change the amount of time to double our money? Well, what would change in the problem? This 10,000 would become $1 million, right? And what would the other side of the equation become? Not 20,000, but 2 million, right? But when you do your division, don't you still get 2? Wouldn't you still get 2 here when you divide both sides by $1 million? And so the rest of the problem would work out the same way, which means that it doesn't matter how much money you put in at the beginning. If someone gives you what the interest rate is, everybody is going to take the same amount of time to double their money. whether it be $1 or $1 million. Everyone is it's gonna take them about 15 years for them to double their money. Okay? So it's kind of like independent of the amount of money you put in, which is kind of interesting. All right. Let
I
me
had
see
a question.
I'm sorry?
I had a question. So
Yeah.
with the 14.58 be our final answer, would we have to say like 15 years as our final answer?
I would just put 14.8 years. I mean, I would like for you to put years because the original problem is a word problem and it's asking how long. So if you just say 14.85, you know, you're right, but 14.85 months, days, you know, so you should specify the time period, even
So
though
we
it's
wouldn't have to like round up, right? To like,
you don't need to round. I mean, you don't need to round. You could. I wouldn't mind if you said 15. I'm going to be more concerned that you did this work properly. If you take that and say 15 years, that's fine. Yeah. Okay. Just looking here. Go ahead.
Is an APY the same as what you're talking about?
Is the what?
APY.
Okay, annual percentage yield. Yeah, well, there's with banks, there's an APR and APY. There's two different things. They're very similar to one another. Annual percentage rate, annual percentage yield. Just generally speaking, that's what we're kind of talking about here. This 4.75 is like an APR. So if we go back to that website, look at this. Let's say that we were to do this CD right here. Well, let's see. Can we find what's the highest we can find? Oh, Ally Bank. You can get 1% off any amount of money. You don't have a minimum deposit, any amount of money, 1%. So I'm going to just run through that problem real quick, 1%. And we're going to do it for 5 years. I just want to know how much money we would have. So let's say that we had $5,000 at 1% for 5 years. That's what that bank's offering us. So we're going to do $5,000, 1% in 5 years. Now, in this problem, we're actually not going to be using the natural log. Okay, we're not, because this is 5,000. We have that. We have E, R is 0.01, and then we have the 5. See, we have everything. We have the rate and the time. And what we're trying to figure out is how much money we would have. So just get on your calculator and do that. I think you're going to be disgusted when you see this. About 3.6. So think about that right now. If you went to this company, Ally Bank, right, which is offering the best out of all these banks, they're offering the best for a CD. They'll give you 1%. Then if you give them $5,000 and you let them have that money for 5 years, not come back for it, then at the end of those 5 years, they're going to hand you $5,256. So you will have made $256, right? Over 5 years, right? That's like how much? 250, what's 250 divided by 5? 50? You made $50 each year. We divide that by 12. You made $4 a month off your money. Every month, they were paying you $4 to borrow your $5,000. Not good, right? Not good. Not good. You know, back in the early 2000s, okay, and I know some of you were probably infants, if maybe not even born, but in the early 2000s, you could get you could get 3% back on your money, not 0.3, not 0.03. You could get 3% back on your money by having it in a checking account. Not even a savings account, a checking account, which means you can take money out of it as you wish. So at the end of the month, they would look and see how much money you have, they give you 3%. Crazy, crazy. Now you can't get, you know, interest rates for checking accounts. I know this because, let me see if I can find interest rates for the best we can find. There we go. 0.1%, 0.1%, 0.25% is the best I'm seeing here. Oh, look at this one, 1.2. That's actually not bad. 1.25. Wow. I mean, we still know it's not that great because they're only going to probably give you a couple of dollars a month, but it, oh, look at this one. Wow. Interesting. Yeah. So you know, back in the early 2000s, I had bought a house and I sold it and I took all the money that I made off that house and I put it in a checking account. Well, I built another house and just that money sitting in the checking account, I made like $10,000 off of it. It took me like 6 months to build the house, 8 months to build the house. And in that time, I made like $10,000 off the money I had sitting there, which was crazy that I could do that because it was just sitting in a checking account. It's crazy. Those days are long gone. Okay. What do we want to do next? All right, so there's a couple of other equations that I want us to be able to solve. So the main idea from this, the main idea that I hope you've taken away is that if we have e to anything, right, equals some number, let's just, you know, 5 or whatever it is, the way that we attack this is we go natural log on both sides, right? And that will drop whatever that thing was, it'll drop it down and then we just keep going, right? Like that's the main idea behind this so far. But now I want to show you a slightly different type of equation. Okay, this is a new type of equation. This is called a log equation or logarithmic equation. And your first example would be this. What if I tell you that when you take the natural log of some value x, you get 5? So I've already given you an example like this. E to the x equals 5. That problem right there, everyone should be able to do because you just do the natural log on both sides, right? But this one, I'm telling you that the natural log of some number is 5. What's the number? So I'm going to go back to these properties I gave you. Remember these properties? Right here. We've been using this one because we've been doing the natural log on both sides. Now we're going to use this one. This one says that if you put e together with the natural log, they kill each other off and you get just the x. So if I go back to this equation, the way we're going to do this is as follows. We are going to do e on both sides, but watch the way I do it. I'm going to do e, and I'm going to raise that to the natural log x, and on the other side, I'm going to do e and raise that to the 5. Now, the reason I'm doing this, e on both sides, is because the e and the natural log kill each other off, and you're left with just the x. And then on the right side, we do e to the 5th, and that we can do on our calculator. So now we're using the e button, the e key instead. And that is a big number. That's 148.4. Does that make sense, everyone? We're going to do another one, but any questions? How about this one? 3 natural log of x plus 1 minus 4 equals 27. Okay, so I've gone crazy now. We've gone from that first example. Now I'm throwing something really crazy at you. Just like we did before, I would like to get this natural log of x plus 1 by itself. Okay, so can we get that by itself? Well, first thing we do is add 4 to both sides. So this is a common sort of theme. We're trying to isolate this thing, and then we're going to use the properties in a second. So I add 4 to both sides. I get what, 31. And can someone tell me what I should do next?
Divide by 3.
Get that 3 out of there, right? Divide both sides by 3. Okay, let me just bring this here. That'll be natural log of x plus 1 equals 31 divided by 3. So we get on our calculators, we're going to get a decimal here. We get 10.333. I'll just add another 3. And now what? We finally have this thing isolated. Now we do the e on both sides. Okay, so now we do e raised to the natural log of x plus 1 equals e raised to the natural log of, sorry, not natural log, e raised to the 10.333. The natural log, what's that? Is that a question? No? The natural log and the e kill each other off. We're left with what was inside that natural log, which is the x plus 1. And then on the right, we're going to get a huge number. I hope your calculator doesn't freak out. Ooh, it's pretty big. Okay, 30,730.16. One more step. One more step. What is it?
-1.
-1. Subtract 1 on both sides. So you get x is equal to 30,729.16. Now we're not going to be using this technique as much, like in fact for the word problems, not today. Okay, so we're coming to the end of class already. We will solve log equations like this next time, because we're going to be looking at things like word problems that involve pH scales for like acid and base chemistry stuff. Let me tell you right now what your homework, what I want you to do for homework. For homework, we're going to go back to the packet. I want you to look at page 155. And let's see, problems 1 through 8. Do 1 through 8. Thirteen through 18. Yeah, that should be sufficient. Those are the types of problems that you'll see on your next exam, which by the way is scheduled for the 24th, which is next Tuesday, right? Is that right? No, not next Tuesday, the following Tuesday, right? So we still have a little bit of time. We've talked about exponential functions. We've already had a test. We've already had a test. No, what was our last test? Hold on, I need to go back and look. I've lost track of myself here. Did our last test cover? Whoa. Okay, I'm way lost now. I don't know how that got so messed up. What did our last test end at? I forgot.
I know we took it on the November 3rd, but I don't remember the concepts that we covered.
Yeah, let me see.
We
I'm in-
did rational functions.
We did, right? Okay, that's what I was curious. Oh, here it is. Let me just look at it real quick. We did rational functions and quadratics. Yep. Okay, so we got all that done. Yeah, that's what I thought. I just didn't want to say that we had covered it already. So yeah, so we've already covered polynomials and rational functions. The next test will cover exponential functions, inverse, natural log and E, which page 155. See, that's what I'm giving you tonight. We still need to come back and talk about two other functions, okay? And then solving and then how we solve equations and stuff. So we still have more to do next week, but you can see that this whole next test is going to be over exponentials and logs. Okay, that's what it's going to be over. All right. Does anybody have any questions? You got a homework assignment for tonight? We're good.
I do have a quick question. Is there any way you could send your notes in the chat?
Yeah, let me get to them here. I will do that. Yeah, you know what I'll do? I'll send last time's and today's.
Okay, perfect. Thank you so much.
Let me get them in the chat. So it's today's notes. Or that's last time. Does anybody have anything else you want to ask? Okay, first that's last time. And that's today. So those are in the lecture notes for you, or in the chat for you.
Okay, thank you so much.
No problem. No problem. Okay. Yeah, that's it. It's 10:40. We'll cut it a little short today. You all have a great weekend. Do your homework. Okay. Make sure you're using the calculator that you can use on the test. That way, you don't run into any issues, and we'll come back and we'll move to the next section. Okay. Or to the next topic in this. All right. Have a good day.
All right, thank you, sir.